In this video, we will continue investigating Taylor series. Recall that a Taylor series is a specific way to come up with a power series representation, where for a power series centered at A, the idea is that the coefficient C sub n has to be given by the following formula. And for our upcoming example, let me just make a quick observation that initial coefficient, the C sub 0, is going to be the function value at A divided by 0 factorial, and recall 0 factorial is 1. So the 0 coefficient, C sub 0, is simply the function value at A. And a bit of language, if we are centered at A equals 0, we refer to it as a Maclaurin series. If we're centered at an A value not 0, we call it a Taylor series. So let's determine a Taylor series representation for the function natural log of x plus 1 centered at A equals 1. So recall the formula. The natural log of x plus 1 is equal to the sum from n equals 0 to infinity of the nth derivative of f evaluated at 1 divided by n factorial x minus 1 to the n. So once again, at this point, we have one goal. We need to determine a formula for the nth derivative of f evaluated at 1. And in order to do so, we are going to rely on our differentiation skills, and then in a bit on our pattern recognition skills. So the function we are dealing with is the natural log of x plus 1. And let's just calculate a few derivatives. F prime x will be 1 over x plus 1. And we can think of this as being x plus 1 to the minus 1 power, which is a bit more convenient, we'll see. The second derivative, using the chain rule, minus x plus 1 to the minus 2. Typically, we would multiply by the derivative of the inside function. That's just 1, so we'll leave it. F triple prime would be minus 1 times minus 2, so a positive 2, x plus 1 to a minus 3. One more derivative should allow us to see the pattern. The fourth derivative will now be 2 times minus 3, which is minus 6, times x plus 1 to the minus 4. So in general, I'm seeing the following. F prime, positive, coefficient, then negative, positive, negative. So we're going to have a minus 1 raised to a power, and because we start off at the first derivative positive, it's going to be n plus 1. Furthermore, we see that the number we have, so 1, 1, 2, 6, and so on. And note that 6 is really 3 factorial, 2 is 2 factorial, 1 is 1 factorial, 1 is also 0 factorial. So the pattern would be n minus 1 factorial, because when n is 4, we have 3 factorial, 1 less. When n is 3, we have 2 factorial, 1 less. And then we also have an x plus 1 raised to a power. The power that we are raised to for the first derivative is minus 1, second derivative is minus 2, third derivative is minus 3, nth derivative should be minus n. So the nth derivative evaluated at 1 is going to be minus 1 to the n plus 1 multiplied by n minus 1 factorial. Raising to the negative nth power is dividing by the nth power, and 1 plus 1 is 2. So using differentiation and pattern recognition, we have come up with a formula for the nth derivative evaluated at 1. However, there is a very important observation that we have to make. This formula does not work in the case when n is equal to 0, for two reasons. Minus 1 factorial is not a quantity that's defined. And plus, if we look at the function itself, the 0th derivative, when we plug in 1, we have natural log 2. So how we will go about this is we will first plug in 0, and when we plug in 0, it just becomes the function value at 1, as we observed in our previous slide. And then we'll add on to this what's happening from n equals 1 to infinity. So the function itself doesn't follow the pattern, but that's okay because we can easily plug 1 in. F of 1 is the natural log of 2. And then for the nth derivative evaluated at 1, we'll simply take the formula that we've generated and plug it in. So that would be the sum from n equals 1 to infinity minus 1 to the n plus 1, n minus 1 factorial. We're dividing by 2 to the n, and we also have an n factorial already in the bottom. And this is all multiplied by x minus 1 to the n. And at this point we have a perfectly good representation of the Taylor series, but at the same time it's always worth taking a moment and doing a bit of algebraic simplification when that is possible. And as we've seen previously, an n minus 1 factorial over an n factorial is something that does simplify nicely. So recall, and I'll write it below here, n factorial is n times n minus 1 factorial. So if we're dividing n minus 1 factorial by n factorial, those n minus 1 factorials cancel, and we're simply left with 1 over n. So slightly more conveniently, we can express this as minus 1 to the n plus 1 divided by n times 2 to the n, x minus 1 to the n. And this would be our Taylor series representation for the function the natural log of x plus 1.